Good morning, everyone. Thank you for joining our session today. I'm Saranya. I lead the data science team in Esri India, and I'm so excited to discuss about the spatial statistics tools we have in ArcGIS. So let's jump right into our session. So ArcGIS has spatial statistics tools for analyzing spatial distributions, patterns, processes, and relationships. Unlike traditional non-spatial statistics methods, these tools incorporate space directly into their mathematics. So they take into consideration proximity, area, connectivity, and several other spatial relationships. So we'll be discussing about the tools you're seeing in the screen right now. So this is our spatial statistic toolbox, which has 5 different tool sets under it. So if you have a data set and you would like to quickly evaluate, is there a pattern or not in my data set, then you will use analyzing pattern toolset. If you're looking for identifying hotspots, cold spots, outliers, then you will be using the tools under mapping clusters. If you are interested in measuring geographic distributions, where is the center, what is the orientation of my data sets, how dispersed are my features, then you can use measuring geographic distributions. Similarly, for predictions, you can use tools under modeling spatial relationships. We also have utility tools, which are miscellaneous tools that can help you with your statistical analysis. Since there are so many tools in this toolkit, we have unlimited time. So we will try to cover most of the commonly used tools in everyday analysis. We will try to address what would be the right tool, how to identify the right tool for your data set, and we will try to also understand what actually goes at the back end for some of these tools so that you can make an informed decision on how to tweak the parameters, which is the right algorithm for my data set. So today's agenda, we will discuss about clustering. We will discuss both statistical clusters, machine learning clusters, and since everyone is interested in predictions, we will also discuss that in today's session. And finally, we will see how you can analyze space-time data. If your data set has a lot of time attributes associated with it, how we can analyze that. So the first topic of the day is clustering. So what is clustering? So clustering is a very natural phenomenon, something we do on everyday basis. When someone presents us with a map with lot of point features, our brain automatically tries to identify the areas where the points are clustered together, right? So in ArcGIS, there are two ways you can carry out this clustering analysis. One is statistical clustering and another one is machine learning clustering. So when we talk about statistical clustering, at the heart of it is null hypothesis. So what I mean by this is, let us say I have a jar of marbles with numbers on them. If I shake up that jar and throw the marbles on the table, what are the chances that all the high numbered marbles to get pooled in one corner of the table like this? Even if you're not familiar with null hypothesis or not familiar with statistics, you can intuitively say that this cannot happen randomly. There must be something going on under the hood or the back end that is causing this pattern to appear, right? So this is what we are trying to do in statistics also. We are trying to identify what are the chances this particular pattern is happening due to random chance, or is there something that's going on behind? Or is there any spatial concept that is causing this pattern? So to answer this question, we use z-scores and p-values. So z-scores are the standard deviation from mean, which means that how far away your data is from the mean value. And p-values are the probability that the particular pattern is happened due to chance. So when you do statistical analysis, you will get a report like this, which says that z-score, there is a less with a certain z-score, there is less than 1% likelihood that this pattern could be the result of a random chance. So if we come back to the slide here, if any of your feature has high z-score with a very low p-value, which means that there is there is a 99% chance that this did not happen due to random chance. So all these values that are pooled on the tail, they become your hotspot. If you have a high negative z-score with a low p-value, they become your cold spots. So the first tool we want to discuss today is hotspot analysis. So what this tool does is it tries to identify statistically significant hotspots and cold spots using the GETIS or GI star statistic. So what do I mean by that? So this is my study area. I have lot of polygons. So each one is a feature and each feature has a value. And this feature also has a neighborhood, meaning there are several adjacent polygons surrounding it. And this is my whole study area. So in statistics, the question I ask is this neighborhood significantly different from the study area? If it is significantly higher, I will mark that particular feature as a hotspot. And I keep asking this question and move to feature. And finally, we assemble or collate all these into a hotspot map. So this is how the algorithm actually works. If the feature is significantly higher than its neighbors, it gets marked as a hotspot. If it is significantly lower, it gets marked as cold spot. So how do we know it is significantly different? This is where our z-score and p-values, which we discussed in the previous slide, come into place. One more point to bring to your attention is the question, where are the hotspots does not necessarily mean the same as where are the highest values. If you're interested in finding only the highest values, you can easily create a heat map to see where you have high values. But what we actually do in hotspots, it's we are trying to find high values that are surrounded by high values. So hotspot analysis is more about the neighborhood than the feature itself. So the hero of our story is neighborhood in statistics. So since neighborhood is very important, how do we determine the neighborhood sizes? Like, how did you decide that you have to consider only this extent and not this extent? So to decide these neighborhoods, we have several methods. In ArcGIS, you have options to go for fixed distance band. So what fixed distance band does is, so let us say that you start with a 5 kilometer fixed distance. The algorithm will create a band of 5 kilometers, and all the polygons whose centroid lies within this band will be considered as a neighborhood. Or in case of points, all the point features which lie within this fixed band will be considered as neighborhood. So this will keep going for this. This is how it decides the neighborhood for each feature. The second method is contiguity edges, where all the polygons whose edge is touching this feature will be considered as a neighborhood. If you want to include the corner polygons also, then you have edges and corners method as well. So in addition to this, there is another method, k nearest neighbors. So this algorithm chooses the specified number of closest neighbors. So let us say that you have a point data set of varying density. You have high density regions, low density regions. K nearest neighbors helps us ensure that there are same number of points in your neighborhood. So if you're working with data sets with varying densities, you can consider using k nearest neighbors. The final method is network spatial weights. So if you think about it, if you're working with data sets about store revenue, or you're trying to identify store closure rates, the nearest store to your store of interest, the nearest neighbor in a fixed band need not be the nearest neighbor in an actual network. So this network spatial weights consider the network distance. So we have a tool called Get Spatial Weights from File, which will help you incorporate these into your analysis. Now let us see a quick demonstration of how you can do hotspot analysis in ArcGIS Pro. So here I have zoomed to Mumbai region. Here I have information about property data. So when you see the attribute table, I have information about all the properties that are listed for rent. It has information about what is the area footage, how many bathrooms, bedrooms are there. In addition to this, whether the particular uh, property is furnished or unfurnished, what is the locality, so on and so forth. So if you want to identify areas where high price properties are together, then you can do a quick hotspot analysis. So the GETIS or GI star statistics, which we discussed in the slides, this is where we are using it. So this tool is very simple, straightforward. You must have already used it. So for input, you call the feature layer of interest. Input field will be price, as I'm interested in finding high priced hotspots. You can, so the conceptualization of spatial relationships is which we discussed just now. So you have fixed band distance, k nearest neighbor, get spatial weights from file. All these options are available. So based on your data set and based on your question, you can decide on which spatial relationship you should go for. And you can also give the number of neighbors you would like to consider. So once you run this tool, automatically you get a hotspots and cold spots in your study area. So here we have regions of high priced properties, we have regions of low priced properties as well. And you can quickly look at the histogram to understand your data better. In ArcGIS, in addition to hotspot analysis, we also have something called optimized hotspot analysis. And when I started using these tools, I always had a confusion when to use hotspots and when to use optimized hotspot. So if you see the toolbox here, you can tell that optimized hotspot has lot of intelligent defaults. So if you go back to our hotspot analysis, you have to decide what spatial relationship you should look for. You have to give the number of neighbors that the tool should consider. Whereas in optimized hotspot analysis, you just have to give the analysis field and the tool will automatically try to identify the right parameters for your data set. So if you're working with data sets which you are not very familiar with, or you're seeing it for the first time and you don't know what would be the right fixed band distance or what would be the right number of neighborhoods to give, in that case, you can go for optimized hotspot analysis. And you can see that as the tool runs, it gives us a detailed assessment of the data. What is the minimum, maximum, mean values? Are there any outliers? So all these messages will get generated automatically. So all the tools in spatial statistics toolbox will give you a detailed messages. So I would highly encourage that you read about these messages as you run the tool, which will give us some insights about how you can fine tune your tool or how to fine tune your parameter or get better results and insights about your data. There is also another difference. So if you like to have a lot of control over these parameters, then you can go for hotspot analysis. But if you are not familiar with the data set, then I would suggest you can start with optimized hotspot analysis. Another feature which I like about optimized hotspot analysis, it lets you work with data set aggregation, which I will show you in the next demonstration. So here you can see that the red output features represent hotspots where high price values cluster together. So this is where you get, this is how the output would look like for this. Now let us go to a data set in Bihar. So here I'm not interested in getting hotspots for my points, but I would like to carry out this analysis on a village level. So here I have the village boundaries in Bihar. I also have information about medical infrastructure that are available within the state. So if I want to identify are there any regions which has very poor medical infrastructure, then I can quickly do a hotspot analysis. And here, instead of the value field, I will be using the counts because I'm interested in the count of infrastructure. So optimized hotspot analysis tool lets you do this aggregation on the fly. So you can aggregate these points into a fishnet grid or hexagon grid or to your polygon as well. If you select this aggregation polygon, you will be given the option to use your own polygon layer. So in this case, I'm using a village boundary. Whereas in hotspot, you will have to do the aggregation first and then move on to the hotspot analysis. Optimized hotspot is allows you to do it on the fly. So when you run the hotspot analysis here, you get output like this. So you can quickly find areas, cold spots where the medical facilities are very less. So these are the areas that would require immediate attention. Now, I hope the hotspot analysis is clear. Let's go to our slides to discuss the next topic, which is outlier analysis. So we have a tool called cluster and outlier analysis, which identifies not only hotspots and cold spots, but also identify are there any spatial outliers. And this tool will be using the answering local Moran's eye statistic. So here also we have the feature, neighborhood, and study area. But the question we ask is going to have another aspect associated with it. We are asking, is this neighborhood significantly different from all the other neighborhood? Is this feature significantly different from all the other features? So these questions can have an yes or no answer, and this yes or no can lead to four combinations. So all the answers can fall into any of these four quadrants. So a feature is higher than other features, and the neighborhood is also higher than other neighborhoods. So this will be a high cluster. Then the feature is lower and the neighborhood is lower. That will be your LL or low cluster. What what is interesting is the other two quadrants where the feature is higher but the neighborhood is lower. So what is happening here is we have a high valued feature which is surrounded by a low value feature. Similarly, LH cluster is where your feature has a lower value and surrounded by higher values. So this will be your hot spot, this will be your cold spot. These two are our outliers. So why would you care about outliers? Like how can it help you? So to discuss this, let us go back to our property data in Mumbai. So here I want to identify, are there any low priced properties surrounded by high priced properties? So that would be a good insights. If I'm looking for a place, I would like to live in a good neighborhood where the property value is high, but I would like to pay low rent. So in this case, we are using the same input. So I have given property data layer as my input. The input field I am interested in is price. And here also you can choose your concept, the spatial relationship concept, and you can run the tool. So this tool will automatically tell you what are all, are there any outliers, where are the high clusters, where are the high low clusters. And don't forget to look at the messages when you run the tool. And here you can see we have high, low, high, and low cluster. It also gives you a very good Moran's scatter plot. So what we just saw in this slide, it's the same plot presented in ArcGIS Pro. So low high clusters. So this could be a property which is low priced, surrounded by neighbors of neighborhood properties which are high priced. So you can see if this analysis would be useful to you. So if you're working with any sensor data and you think you would like to identify is there any faults in your sensor, you can use this outlier analysis to identify them. Now that we are done with our inferential statistics or traditional statistics, let's move on to machine learning statistics. So in machine learning, you can cluster your points based on just location or values. So location would mean like accident locations or incidents of fire. So those would be a location-based clustering. Value-based clustering will be useful when you're trying to understand income or education or literacy rates. So if your data set has values, you can use algorithms to cluster your data based on values. We have options to combine these two. You're interested in clustering with a spatial contiguity, then you can use location and values, and you can also add time component to it. So the first tool is density-based clustering. So it tries to identify clusters based on the feature locations. So under this density-based clustering, we have three algorithm options: DB scan, which is also known as defined distance, HDB scan, also known as self-adjusting, and optics, also known as multi-scale clustering. Uh, we will discuss this in detail. I would like to tell you that DB scan and optics all can work with time also, whereas HDB scan cannot work with time. So if your data set has a timestamp, then you should consider going for DB scan or optics to get the most value of your data. So DBSCAN stands for density-based spatial clustering of applications with noise. So what it does is it groups the points as clusters wherever it finds high density region. If your point is in low density region, it will mark them as noise. So if you remember in our previous statistics, we were talking about neighborhoods, right? So here it is all about the density. So let us assume this is your point features and all the high density regions will be clustered and all the low density region will be marked as noise. So here, instead of neighborhood, we are talking about density. So how do you define a high or low density region? So for this, the algorithm uses two parameters. One is search distance and another is minimum features per cluster. So let us say that I want to identify a cluster. The cluster should have minimum 5 features and it should be within a distance of 5 meters. So my search distance would be 5 meters. If I can find all these 5 points uh, within uh, if I can find all these 5 points, that distance will be my core distance. If the core distance is less than search distance, that would be a high density area. If the core distance is greater than the search distance, that would be a low density area. So that's the same concept we are using here. I hope I didn't confuse you much. So basically, so this will be high density and this will be regions of low density. And let us take the same parameters. Say our search distance is 5 meters and I need at least 5 points in my cluster. And I would also like to include time. So when you say time step interval to consider is 4 days, what the algorithm will do is it will only consider the points. So let us say this is the point I'm starting with. It will only consider the points that are 4 days before and after the timestamp I have suggested. So it will drop all the other points that do not fall into this time interval. And after filtering out, again, the core distance and search distance will come into place and the clustering will be done. So this is very easy to this tool can be very useful when you're trying to find out any event that is happening within a particular time interval. Moving to HDB scan, also known as hierarchical DB scan. So in our previous method, which is which is DB scan, the user of the tool needs to suggest what is the search distance, and user should suggest what is the number of features or minimum number of features in a cluster. Whereas in HDB scan, it is completely data driven. The model will try to identify the search distances and the number of clusters by itself. So it is completely data driven. So what it is capable of working with data of varying densities. So that is why we call it as self-adjusting, because it on the fly it can decide the right search distances and number of clusters. The final algorithm is optics, which stands for ordering points to identify cluster structure. So what optics does is it will order your data sets in a particular reachability plot. So what it does is it takes all the points and it orders them. We call it a reachability plot, and each point is associated with a reachability distance. So reachability distance is a measure of how easy it is to reach that point from other points in the data set. So if you look at this, all the valleys will be clusters, all the peaks will be noise. So the reachability plot will order them such that, so we have these valleys will be one cluster, this would be another, this would be another, and we have these points which are noise. You need not understand exactly what's going on here. When you look at the demonstration, you will get a good idea about how optics can help us. So to understand the key difference between these three algorithms, DBScan uses a fixed search distance, and it is good for identifying clusters of similar densities. And since the parameters are already set, this algorithm is much faster compared to the other two. Whereas in HDB scan, it uses a range of search distances to find clusters of varying densities. It's completely data driven and requires the least input among these three algorithms. And optics, it uses the concept of reachability plot, and this is very useful to fine tune your clusters. Since we are trying to identify the distances of each point and reachability distances, this can be computationally intensive. So if you have time in your hand and you would like to do a very good clustering analysis, optics would be a good place to. So let us see a quick demonstration of densities. So I'm in Bangalore right now, and here I have information about the pickup locations of cabs in a time span of 2 to 3 days. So each point is a pickup location. And let us say that I would like to do a clustering of these points. I need to identify clusters which have at least 50 pickup points in a radius of 500 meters. So I can give all these details and just run the tool. So the algorithm will automatically identify where such clusters are, where a particular company is able to find at least 50 pickups in a 500-meter radius. So this is your density-based clustering, and this will give you the number of clusters the model has identified. Now let us say that I want to add time also into this analysis. So for the same data, if you look at the attribute table, I have a timestamp here. So I have not only the pickup location, but also the date and time of that pickup. So here, what you have to do is in our input will be your data with time. So here I'm interested in finding the same cluster which has 50 features in 500 meters, but I want this cluster to be within 5-hour interval, which means that I want to maximize the pickup points in this 5-hour interval. So when you run this data, the algorithm will try to identify the clusters with not just space, but also the time. So it has identified 2 clusters. If you look at it, so this is actually a Marriott hotel. So you can see there are a lot of pickups surrounding that hotel. And when you open the time span, per cluster. So when you run the DB scan with time component, you get this chart. So you can see that there is a maximum pickup within this uh, time interval. So if I am working with any logistics where I want to understand the effect of time or how I can optimize my pickups or how I can optimize my business timings. So this type of analysis can help us. I think this could be a check-in time in Marriott Hotel. Maybe that's why we are having a lot of clusters in this time window. So this is how you can use a density-based for your analysis. And let us now move to optics. Is my screen visible, Lalitha?
Yes, we can see your screen.
Okay, thank you. I lost signal for a second. Sorry for the interruption. So now let's see about how optics can add value to our clustering analysis. So this is the same data with pickup points of cab locations in and around Bangalore. So here what I'm doing is I'm trying to identify clusters which has at least 200 pickup points in a search radius of 2 kilometers. So when I run this tool, the output I get is this. So when you see, this is the reachability chart I was talking about. So it is trying to order the points in such a way that takes into consideration the proximity of each of these points to other. So if you look at the data set closely, there is this light blue cluster, which is actually very big. I would like to split this into smaller clusters. So what I can do is when I ran the optics earlier, the tool actually suggested uh, the cluster sensitivity it used was 18. So the second best sensitivity is 24. So what I can do is if I want to fine tune this, I can just add the suggested cluster sensitivity here and I can run this analysis again. So when I do this, the model will try to optimize the clusters. So in our previous analysis, if you look at the number of features, per cluster. So there were 6 clusters, and our light blue had 5,023 points. Whereas now, after fine tuning, I have 7 clusters, and the light blue has 3,333 points. So optics is a very good tool if you want to fine tune your clustering analysis. And another quick tip I would like to share is when I ran the tool, you can see this error comes up, right? Problems reading one of 11,017 total records. My guess is there could be some data with null values here. So you can use our data engineering tool, add all the fields and just do a calculate. You can look at the null column. So actually this trip ID has one data which has null value. So you can just select null and delete it, calculate again or null values of one. So this is a very useful tool. And now when you run the same analysis, you will find that that error is gone. So this is just a quick tip I wanted to share. Okay. So that is an overview about density-based clustering. We also have several other clustering methods. So one is multivariate clustering. So what if your data set has multiple variables? So I'm not interested in just the number or count of incidents, or you're not interested in just price of the property. You have several other variables and you would want to cluster them based on all these variables. For example, you have population density, median age, and average income in your data. And when you're clustering, you want to use all these three variables. How do you do that? In this case, multivariate clustering algorithms can help you. So one such algorithm is k-means. So what it will do is it will create a data space. So this is a data space, not actual space. So in this data space, in each axis, we have a different variable. We have median age here, average income here, and population density here. And whatever points we have in your data set would fall somewhere in within this data space. So there could be data with high population density and high median age, but low average income. So similarly, you can add multiple variables to your clustering analysis. We also have spatially constrained multivariate clustering. So while the k-means will partition your data into clusters based on only attributes, this spatially constrained multivariate clustering will partition your data not only with attributes but also proximity. So you can ask for the clusters which has similar values but also spatially contiguous. You're interested in the spatial aspect as well. In that case, you can go for spatially constrained multivariate clustering. So here, the objective of this would be to cluster the points or features such that it is similar within the cluster and distinct or dissimilar between the clusters. We also have a tool called Build Balance Zones, which partitions your data into uniform zones based on feature attributes and proximity. For example, if you have multiple supervisors in your organization and you want to assign them equal number of projects, equal number of projects that require immediate attention, which requires moderate attention, and in which they can take their time. And you also want to ensure all your supervisors get equal number of projects, equal number of area coverage. So in such cases, you can use build balance zones. We also have tools for co-location, which measures local patterns of spatial association between two categories. So how do we do this co-location analysis? For this, I'll be taking crime data in the district of Bilaspur. So here I have the locations where the crime has happened. And I also have information about offense. So if you check the what are all the fields I have here, you can see that I have a field called offense, which you can open and see whether it is gambling or theft. I have information about the crimes and also the type of crimes. Now, my objective is to identify are the crimes of accidents co-located with crimes of drugs and NDPS. In that case, I can go for co-location analysis. So I can either give in two data sets as an input or a single data set. So here I have all the information in the same data set. So I will be using this option. And my feature of interest is crime data. Field of interest is offense. I also have a timestamp. So if I want to identify our crimes of accidents and crimes of drugs co-located within 1 month interval. So these type of questions I'll be able to answer. So here also you have the neighborhood type and you can give the temporal relationship, whether you want to identify before or after, or you can give the time span. So when you run this tool, what the collocation analysis tells you is that it will label the points according to their significance. So if you look at these brown dots, so these are the places where crimes of accidents and crimes of drugs are co-located and their association is very significant. So this could give us insights like if the police department there targeted the crimes of drugs first, chances are the crimes of accidents will also go down. So this is how you can use co-location analysis. Now coming to the next part of our session, which is making predictions. So you all must be familiar with regression analysis, where you try to model linear relationships with data. ArcGIS offers you multiple options for carrying out this prediction. You can have generalized linear regression, geographically weighted regression, multi-scale regression, forest-based presence-only prediction, etc. So generalized linear regression is pretty straightforward. You have an equation, you have a dependent variable, your x's will be your explanatory variables, you have your coefficients, which is beta, and you also have your residual. So residual is the difference between the observed value and the predicted value. It helps you understand whether it is overfitting or underfitting. Uh, so when you do a generalized linear regression, your whole study area gets one equation, but chances are that it may not work in some cases. For example, if I do an analysis in Tamil Nadu, the equation that fits the plains of Trichy will not fit the hills of Nilgiris, right? So geographically, we might need different equations. So geographically weighted regression will give you different equations for different features. And here also we have the concept of neighborhood, and ArcGIS offers you different types of neighborhood selection method. And you can also add multiple explanatory variables in this GWR analysis. And we also have multi-scale GWR. The difference between these two analyses is the neighborhood size or the distance band for all the explanatory variables will be same in case of GWR, whereas in multi-scale GWR, you can have different neighborhood sizes. Why is this important? So if you think about it logically, the property prices might change in a 5 kilometer radius, but temperature may not change in a 5 kilometer radius, right? Temperature would require bigger search distance. So each spatial phenomenon might have a different scale or different scale of neighborhood. So multi-scale GWR gives you that flexibility. So let us see a quick demonstration of that. So now we are back to our prediction. So here I have the same data, so property data layer. Here what I'm trying to identify is I'm going to try to get an equation which will help me predict the prices for new locations. So here I'm using the tool multi-scale geographically weighted regression. So here I have the dependent variable, which is price, and explanatory variables, area, bedroom, numbers, floor count, etc. So when you run the tool, you automatically get information about the significance of each of these variables. So this tool will give you an output which looks something like this. So when you go to area, you can see where the area attribute or area variable is significant and where it is insignificant. If you move to this particular location, I'll just link all these together. Yeah. So in this location, area seems to have more influence, and floor count and number of bedrooms, not so much. Similarly, if you move to the region around airport, you can see that area plays a very significant role, whereas floor count seems to have significance on one side and not on the other side. So this is how you can try to interpret your data. And MGWR also gives you standardized residuals, which is the eta we saw in our slides. And it also gives you a scatter plot of relationships between multiple variables in your data set. Now, next I would like to talk about forest-based regression. So most of you might be familiar with random forest. It's the same concept. It's the same algorithm. So here what I'm trying to do is I have a training data. So all these are locations where I already know the price and I already have information about all the explanatory variables like area, whether the apartment is furnished or not. So, and I want to predict, look, what could be the prices in these regions. So for this, I will be using a forest-based classification and regression. It gives me option to only train your data or to predict or to predict to raster. We have multiple options, but I like to carry out this analysis in two steps. First, I will train it multiple times. So once I think I have a good model, I go for prediction. So here the input data is property training data, and I want to predict the price of the property. And the variables I'm using is area, number of bathrooms, number of bedrooms, and latitude, longitude. So you can add categorical variables also here. So once you have categories, automatically the category will be selected. So what this tool does is it trains the model and gives you an output file, which is called as SSM or Spatial Statistics Model file, which you can use for your analysis. It also gives you a summary of variable importance, so which has most influence on the price. For example, area has the most influence in determining the price in a study area, followed by the number of bedrooms, and then you have the location information. So let us see that. So once you have trained your model, you can go to predict models using spatial statistics file. So once you run the tool, this is how the SSM file would look like. And let me just choose the right model file, and automatically the other variables will get auto-populated. And if there are any changes, you can always use the drop down to match the fields. So here we have used the training data, and I need to predict what could be the prices in this. So my input features will be this to predict layer, and output is here. So when you run this tool, this is the output I get. So when I look at the attribute table, I have a new field called predicted price. So I have also added the real price, so you can look both of them side by side. So this is our predicted price, and this is our real price. Okay. So here the prediction is 1,24,000, and here the real price is 1,25,000. So you can keep on fine tuning this model until you have a good prediction model. Now I'm going to deviate a little bit from our spatial statistics tool and talk about one tool called AutoML. So this is under GeoAI tools in ArcGIS Pro. So if you have ArcGIS Pro Advanced, you can access this GeoAI tools. So we saw so many models and so many hyperparameters, right? If you don't know what would be the right model for your area of interest, what you can do is you can run this AutoML tool, and the model will try to generate a report like this. It will test your data set with multiple models and multiple parameters, and finally suggest you the best model. So this report is self-explanatory. Each model has confusion matrix, what is the learning curve, so what is the ROC? So it will give you detailed information about why it chose that model as the best model. So if anyone is interested in exploring this further, you can let us know in the chat box so we can plan our future sessions along these lines. So this is the same analysis. So just like forest-based forest-based prediction, we have separate tool for training and separate tool for prediction using AutoML. So what I have done here is I have information about functioning of water pumps. So let me just zoom. So here in West Bengal, I have information about water pumps and whether they are functional or not. And this data set has several explanatory variables like how many households are there and what is the year of construction, what is the age of those particular water pump, and whether what is the water quality or turbidity levels there. So it has multiple information. My objective now is that we have few more pumps in this area. I want to predict the overall status or the working of the pumps in this area. So for that, I have I have trained the model using AutoML, and I have also predicted using AutoML. In addition to the explanatory variables, which are latitudes, water points, constructed here. I've also added two more rasters, which is maximum temperature and precipitation in this area. You can also add a distance component. So if I have added here the freshwater sources that are available in this area of interest. So this distance features also you can add. So once I predict using AutoML, so this is the output I get. So the algorithm is it can predict now whether given all the other variables, whether a particular pump is functional or not. So this is about AutoML. Finally, I would like to talk about space-time cubes. So when we started the session, I promised that we'll be discussing about the space-time data also. So what I have here is we are looking at the groundwater data in the state of Telangana. So each of this point represents a value about depth to groundwater level. So these are meters below ground level. So you can see that each of these values also have a date associated with it, which means that if I look at the data engineering and do a calculation in the date field, I can see I have at least 24 unique values, which means that I have 24 months worth of data in this particular data set. And it is from January 1st, 2021 to December 2022. So that is 24 months data for you. So when I look at the data, I'm not able to interpret it that much, right? So this is where space-time cubes can help. So what I'm trying to do is I'm trying to build a space-time cube with three values. So I have my x-axis, y-axis, which is your latitude and longitude, and I'm also adding a third axis, which is time. So I have the data set for all these locations for different time periods also. I'm trying to aggregate them into bins. So just like how we saw neighborhoods in our previous analysis, here also we will have multiple neighbors. So each of this is a bin location, each of this is a time slice, and using this, I can have spatial neighbors, space-time neighbors, and also temporal neighbors. So you will understand it better in the demonstration. So what I'm trying to do is I will first create a space-time cube. So my input will be this point feature layer and time field is date. And here I can aggregate this point into a fishnet or defined locations. Here I am aggregating it to the sub-district boundaries. So I can make this analysis on a sub-district level. So when you run this tool, it creates a net CDF file. And to visualize this file, you can run either visualize spacetime cube in 2D or visualize spacetime cube in 3D. So both these tools are available in spacetime pattern mining tool sets. So let us first take a look at spacetime cube in 2D. So what it does is it aggregates all the data into the bins we saw earlier, and here it has aggregated into bins corresponding to the sub-district boundary. When you click on any of the polygons, you can see the actual trend. So these purple polygons have an uptrend, whereas the green ones have a downtrend. But even here, I'm still not able to visualize how the data is changing in space and time. So what I'm trying to do here is I ran the visualize space-time cube in 3D, and the same has been added in this. So let us zoom to that layer again. So here I have my data as a 3D cube. So for each location, you can see the values. You can also open the visualize 3D chart to see the data sets. So the bottom ones are the oldest data and the top ones are the most recent data sets. So here I have data till December 2022. So there is another tool called emerging hotspot analysis, which is especially made for identifying hotspots in space-time cube dataset. So if you have such NetCDF dataset, you can use emerging hotspot analysis. Let us take a quick look at how the output looks like. So the interpretation here is going to be a little different from what we saw earlier. So here it is useful to look at the messages. So here you can see that we have different categories. So when I expand this output, I have new hotspots, consecutive hotspots, persistent hotspots, etc. Let's take a look at some of the data sets. So let me just move to a new hotspot. So new hotspot means that the most recent time interval is hot for the first time, which means that nothing significant was happening here for a long time, and suddenly this has become a hotspot. So when I add the space-time cube layer on top of it, you can also see why that particular classification was derived. Similarly, a cold spot is where nothing significant was happening, but recently it has started to become a cold spot. And if you look at this place, we have persistent hotspots, which means that 90% of the time the values has been hot. So if I look at persistent, 90% is hot, but there is no trend up or down. So when I look at the values, I can say that almost 90% is on the higher side, and there is no particular trend. So emerging hotspot analysis is one way to quickly understand this one. Just like our 2D data, you can also do outlier analysis in space-time cube as well and visualize the data sets. And we have a add-in for Spacetime Cube Explorer. So what it does is it lets you slice through this data set. So I will try to put the link for this add-in below. So what it lets you do is it lets you filter your Spacetime cube so that only the cubes which have your data of interest pops up in the scene window. So this is useful when you're trying to slice through and look into your space-time cube, actually what is happening. If I change it to the local outlier analysis, I can actually see that these are the outliers, and you can see whether it was an outlier in time or space. So these type of analysis can be done. In addition to this, space-time pattern mining also has tools for forecasting of values. For example, if I want to predict the groundwater quality trend in future, I can use multiple methods. I can use curve fit, evaluate exponential smoothing, forest-based, and I will just quickly show you one of these tools because I think we are almost to the end of the session. So use this. So you can go for curve fit forecast. So in this time series forecast, the input will be the space-time cube, which we created using create space-time cube tool. Analysis variable will be mean or maximum. You can choose any of these. You can define the number of time steps you would like to forecast. So here I would like to forecast it for 6 months. You can give a name for your output also and just run the tool. So what this tool does is it tries to create forecasts for each of these locations. So when you click on any of the polygons, you will be able to get the exact equation or forecast for here. So here up till this vertical line here is the original value. Whereas after this line, we have a forecasted value, and this area region represents the standard deviation. So you can see that we have multiple outputs, and this is the output from exponential smoothing forecast. So, with this, we have come to the end of the session.